the stress and strain curves. In a standard test of tensile properties, a wire is stretched by an applied force, and the fractional change in length, the strain, and the applied force needed to cause the strain are recorded. The applied force is gradually increased in steps, and the change in length is noted. A graph is plotted between the stress, which is equal in magnitude to the applied force per unit area on which force is applied, and the strain produced. A typical graph for a metal is shown. These curves helps us to understand how a given material deforms with increasing loads. Let us understand these curves briefly. The curve is linear and Hooke's law is obeyed. The body regains its original dimensions when the applied force is removed. In this region, the solid behaves as an elastic body. Stress and strain are not proportional. Nevertheless, the body still returns to its original dimension when the load is removed. The point B in the curve is known as yield point, also known as elastic limit, and the corresponding stress is known as yield strength, sigma y, of the material. If the load is increased further, the stress developed exceeds the yield strength and strain increase rapidly even for a small change in the stress. The portion of the curve between B and D shows this. When the load is removed at some point C between B and D, the body does not regain its original dimension. In this case, even when the stress is zero, the strain is not zero. The material is said to have a permanent set and the deformation is said to be plastic deformation. The point D on the graph is the ultimate tensile strength, sigma u, of the material. Beyond the point D, additional strain is produced, even by a reduced applied force, and the fracture occurs at point E. If the ultimate strength and fracture points D and E are close, the material is said to be brittle. If they are far apart, the material is said to be ductile. Stress-strain behavior varies from material to material. For example, rubber can be pulled to several times its original length and still returns to its original shape. Stress-strain curve for the elastic tissue of aorta present in the heart. Note that although elastic region is very large, the material does not obey Hooke's law over most of the region. Secondly, there is no well-defined plastic region. Substances like tissue of aorta, rubber, etc., which can be stretched to cause large strains, are called elastomers.